Okay, so we're going to start the final exam review for EE and CE 3320. Yeah, so I talked to Dr. Balsara, and this is what he said will be on the exam. Will be sequential circuits, 1 and 2's complements, floating point arithmetic, scientific arithmetic, and everything else on there. The bottom two will be on there, but I'm not going to go over it. If you need me to go over it, I can go over it on Friday. Okay, so sequential circuits are pretty simple. They're basically just combinational circuits. You just have a memory element added. So that could be anything from flip-flops, register files, SRAM, I don't know, whatever you could possibly want. You just need some sort of memory element. And then obviously you'll have your regular inputs and your regular outputs as well. Yeah, so a lot of these are used in your finite state machines. Whenever you've done those questions, generally you'll have your memory. I think they generally use register files for those, but you could use something else.
Hey, Rochelle, are you sharing your screen?
Yeah. Are you not able to see it?
No.
But it's right here. Okay. Maybe it's not working in there.
Here, let me join. Oh, I see it. I see it. There we go.
I hope the recording sees it. It's gonna be really awkward. Okay. Yeah. Does anybody need an example? Because I felt this pretty self-explanatory, but if you want, or because I think you want to spend more time on the more difficult questions. But okay, so then next is 1's and 2's complement. Generally in digital logic, you're going to use your 2's complement more than your 1's complement, just because 2's complement is how most people do their negative numbers. So for 1's complement, all you're going to do is switch your zeros to a 1 and your 1's to a 0. You can see that here. And then to go from 1's to 2's, you're just going to add a 1. Any questions on those? Okay. I don't think I put any questions for that, but okay. Next is floating point arithmetic. A lot of people get confused on this, especially in 2310, and I guess now as well. Your first bit, which is, oh, wrong color. Should switch colors. Let's go with that one. Okay. This one is going to be your sign bit. So if it's a 1, that means it's negative. If it's a 0, it means it's a positive. And then your next eight bits here will be your exponent. So obviously still in binary. So you're just going to convert that out of binary and then put that here. And then next up here is your Mantessa. I think that's how you say that. But remember that there is a presumed 1 before it. You just assume that there is a 1. We'll do some questions here in a second. Okay. So we'll start with this one. I'll have everybody try it on their own, and then I mean, the steps are kind of right there, but okay. So your number is 19.59375, and then try to convert that to IEEE standard 32-bit format. Okay, we're gonna go ahead and work on this together. So obviously this number is positive, so our sign bit's gonna be a 0, which is right here. And then we're gonna convert 19 into binary. I'm gonna start with just the 19, and that's gonna be 10011. It's gonna be 16 plus 2 plus a 1. All those two together, all three of those go into 19. Then we're going to go do the decimal. So that's going to be 0.59375. And then that one is going to be 10011. Yeah. So now we're going to go ahead and put this in. So if we go over here, right? Okay. So if we look at this number here, we see in order to get the radix point moved to here, because we, like I said before, there is a presumed 0. So we're going to move the radix point 1, 2, 3, and 4. So that means our exponent needs to be a 4, which is shown up here, because obviously that is a 4. Yeah, so there's that. And then this is the number after we moved it. So we're going to write this over here. And then you can just carry the zeros through the rest of them. Yep. So there's that. We're going to go work the other way around. So this is, yeah, that's going to be a bit of a pain. But if anybody wants to try that, you can go for it. Yeah.
Can you go back to the
Oh, yeah, sure. So obviously our sign bit is 0, so you got that. And then we have our 4. We moved the decimal point 4 places to the left. So the way that this is done is it's kind of like scientific notation, where it's assumed that you'll always have a 1. You'll always start with your ones. Your ones place will always be the value 1, and then you'll have your decimal point and whatever else after that. So because of that, we had to move our decimal point over 4 times. So that's where we got the 4 from. And then we just put everything that's to the right of the decimal in the Mantessa area. If you have a lot of questions about this, I'd say reach out to one of the 2310 tutors, because they can probably help you with this a lot more than I can. Yeah.
So the Mantessa is just with the remaining numbers?
Yeah, basically.
It's like the 32 bits. Yeah. Or is it 16? I'm sorry. Is it 16 or 32?
23.
It's 23. Yeah, it's 23, 8, and 1.
Yeah.
Okay, so this is the same thing, but the other way around. So we see here with the 0 that means it's a positive value, and then we're gonna go grab the next 8 numbers. So it'd be from here to here are your 8, and then the rest of these are the other ones. So this would be 5. Yeah, so 100 is 5. So that means it's something to the power of 5. Right? So now we're going to go ahead and work on the Mantessa. So we have 1101010 at the decimal point. Is that correct? Yeah, that's correct. Okay, so now since it's to the power of 5, we're going to move the decimal point over 5. So 1, 2, 3, 4, and 5. So we'll have 101.10. Does that look right? Yeah, I think that does look right. So this should be our final result. Then if we calculate this into decimal, have a 2, an 8, and a 16. So it should be, I messed this up, didn't I? Where did I go wrong? Oh, right. We remember that there is the 1 that's presumed. So if we add that, that'd be 32. So that would be 58.5, which we got over here. Do you guys want to do another one and just move on?
If you just show it so you can go back in your recording.
Yeah.
So that people can go back in the recording.
Okay. So we see that we have the initial 1, which means it's negative. So we got that. And then we're going to go over here. So we got, let's see, 4 and 4. Yeah, okay. Yeah, so that's 9. And then since this is a negative, we're going to subtract 127, which is 118, which is our exponent. Don't ask me why. It's just how it's done. Maybe the ChatGPT. That's if you want to know why you do that.
Wait, it's not 118?
It is 118, negative 118.
You just wrote negative 1.
On my screen, it says 8.
Oh.
Oh, there it is. Oh, it says,
Wait, what?
okay. This is a lot of lag. Okay, so now if we look at this, we have 1.0001101, right? And then this to the power of negative 118. So yeah, that's your answer. Yeah.
I see, okay. So you just put, since it's a negative, you just put the 1 in front and then you just convert the mantis into decimal, okay.
Yeah.
Okay, I see.
Okay. So you said that's
It's like after,
yeah, you would look up those, the 11 or the 60. You can see those ones.
yeah, so it's 0, 0, 0.
That's the mantissa.
But then you stop counting the 0 that comes through, because it's all zeros after that.
That would be like power 2 to the power of 15. And you have to count that number, right? Like you have to count the number.
Which number?
Like those ones.
In the blue or
In
the?
the blue, yeah, that's what matters, right?
Yeah, that's what matters. So this is what I did. I put the 1 and then I did the decimal point and then I just copied these values over here.
Yeah, that's what that is. So, and then you don't look at everything past the 1, because they're all just zeros.
Yeah.
And then you start, from decimal, you start from left to right instead.
Now, next up is scientific arithmetic. I think this is pretty obvious what it is because you've probably done scientific notation before, but we're going to do addition, subtraction, multiplication, division, and normalization. Yeah, okay, so we'll just move on. So for addition and subtraction, they're basically the same thing. The first step you want to do is make sure you get to the same exponent on each. So 10 times whatever. So since this is a 3, we just moved it up to a 3. Then you're going to add these two together and you're just going to leave this the same. So 2.15 plus 0.34 is equal to 2.84 times 10 to the 3. Okay, pretty simple. Next, we'll go to multiplication. Oh, this looks really weird. Okay, so yeah, so we're going to take these into parts. We're going to do this, and then we'll take these and these. Okay, so with this, we're going to multiply the 3 times the 2, and then we're going to add the 4 plus the 3. So this will give us 6 times 10 to the 7. Okay. Division. The exact same thing, just the other way around. So pair, then pair, and then pair and pair. So this will be 6 over 2, and then we'll switch colors. 7 minus 3, and then this gives us 3 times 10 to the power of 4. Imagine this is just your test.
Bro, if this was our test, Easy.
Well, Star is the nicest professor ever.
It's not.
Yeah. So, yeah, normalization. Yeah, you just make sure that you have a decimal point right there. Cool. Okay, let's go to the next thing. Adders. Half and full adders. Those are the only two that you need to worry about. You don't need to worry about look aheads or whatever. Don't worry about it. Yeah, so all of those can be built out of logic gates. I recommend that you try it to build them out of logic gates. That's at the bottom right there of how to build it. Yeah. So yeah, it's not too bad. So yeah, we'll go here. Oh, actually, I guess we'll go create them. So let's do the half adder first. Okay, so you have one input. We'll call this A, we'll call this B, and we'll call your output Q, and then we'll have a C out. So we know that Q, you'll only get a 1 for Q if it's A exclusive ORed with B, and then this is equal to Q, and then C out is equal to A, B. Yes, for your half adder. So we'll go make this real quick. So this will be your Q. This will be your C out. Okay, any questions? That's pretty obvious. Okay, so I'm just gonna do the full adder here. So we'll still have our A and our B input, but this time we'll have a C in. We'll still have our C out, and we'll still have our Q. Okay. So Q is going to be equal to A exclusive ORed with B exclusive ORed with C in. C out is equal to it's going to be equal to AB plus ACN plus BCN. That looks right, I think. Like, mistaken. Oh yeah, I guess you could do it that way too. Yeah. Okay. Cool. So I guess we'll go ahead and make this. So Q. Okay, can someone tell me if that looks right? I think that makes sense. Okay. Okay, then we'll go over to binary multipliers. These things are evil, but this is a 2-bit multiplier that I built a few days ago. They're not too bad. The main way that I do the proof for them is have your A's and then have your B's, then just multiply together, add these together, and then if you convert this into a circuit diagram. It'll look like that. If you guys want, we can build a 3-bit. It's up to you guys.
Actually, yeah, that would be, what is happening on the left side?
The left.
Yeah.
Okay, so let's do this real quick. So these are just variables. So this is our 0-bit of our A and our 1-bit, and then the same thing for A and B, right? So if we're basically doing regular multiplication, right? So we multiplied this and with that, right? That's how you do it with decimal. So that's what we wrote down here, and we wrote down here. Then we do the same thing for this bit. I didn't write the 0, but you can put the 0 there. And then we multiply here, we multiply there, and then we just do it here. And then we just add going down. So it's A0, B0 plus 0, and then A1, B0 plus A0, B1, and then A1, B1 by itself. Yeah. Okay.
When those correlate to Q0, Q1, Q2.
Yes.
Okay.
So then I followed that whole step to get to here. So we can go create the 3-bit. It's kind of annoying. What's up?
Addition translated to AND and OR gates directly.
One more time.
So the AND and OR operations translated to like or AND and OR gates directly.
Not necessarily. I mean, you can convert them over, but you have to follow a certain process. And then here we use the half adders. I use half adders. You use full adders too, I guess. Well, you need to add these two values right over here, because we added like right here. We added A1B0 plus A0B1. So we need some way to add them. So we use an adder.
Use the half adder.
So if you want, you could convert those into a gate level thing, but it's easier if we just use the box.
So, yeah, those are
Yeah. So
I don't know.
this half adder.
Yeah, is it for,
So it's for the carry of this.
oh, I see.
You have to make sure you remember your carries.
That's very good.
So I guess we can go do the other one. You're gonna have to bear with me on this. It takes a while.
Thank you, bro.
I would recommend doing it by yourself, but because you should learn the process. I was on Do Not Disturb. How am I still getting notifications? Okay. So let's go build this. So I'm going to start from right to left. So we have our A0 and our B0 going into a half adder. The output of this half adder will be our Q0, and then we will also have a C out. No, why am I doing that? C out, and then we'll have another half adder here.
Oh, so you're not using digits at the start?
Oh, my bad. Yeah, you're right.
Also, can you zoom out just a little bit, because I was trying to follow along. So if it's 3-bit, you're supposed to have multiple outputs, because I was like wondering, what do the other ones go to? They used to Q4, Q3, Q2. Okay, I see.
Yep, good catch. Yeah, so this can be A0, B0, and then these will be ANDed together, and that will be your Q0.
Rochelle question.
Yeah,
Are you not like because on the left you didn't put a Q5 for your carry? Is that on purpose?
oh, I mean, I can add one.
Do you need
Oh,
one?
okay.
Don't need one.
You need Q5 because of the area. Okay, yeah. For like overflow, right?
Yeah.
Okay.
Yep. Okay, and that should be your answer.
So for Q2, some of your full adder, and then to a half adder because you have one more input for that carry of the first one. Oh, I see. But then I wasn't alright with that, but
Yeah.
I didn't want to look up and like cheat. But
Well, that full adder, that third input is basically just a carry in input, correct?
For, let me see.
Just a full adder in general.
Oh, yeah, generally, yes.
Okay.
That's all of it. You good for me to move on?
Yeah, I'm good.
Okay, so shifters. Fun times, right? So there's a lot of different types of shifters. You generally will see ripple shifters, but I think the one that they want you to know is this type of shifter. So let's say you have 4 values coming in. So this could be your A3, A2, A1, A0. And then this could be, I don't know, extra. And this will be your extra F. So then we'll have your Q0, Q1, Q2, and Q3. How many bits do we want to shift by?
You're just asking us.
Yeah.
Let's do an odd number. Well, let's do 7, bro. Do 7.
Okay, 1 through 4. 1, 2, 3. Let's do that.
3.
Okay, gotta be difficult, eh? Okay, so now we need extra. So we're gonna go connect these over to this way. And then we'll
Is it
go.
actually called extra, or you just,
I just did whatever I want.
is it normal, just any input?
Yeah, it's usually just input. Sometimes it's just ground, depending on what you want to do with it. And then we need our extra 2. And then we'll do 1 and 0. So the way this shifter works is instead of this bit, which used to be our 0 bit, is now our 3 bit. And then you can do that for however you'd like, however many you want. Obviously, if you have 64 bits, which you generally will, you can have a giant shifter.
This is shifting by what, 2?
3.
3.
What if you want to switch by 1 to 5? Do you need more bits?
I mean, then you can just tie it to ground, right?
Yeah.
Because all of these would just be ground at that point. But yeah, you could. I'd say just get a bigger shifter at that point.
So could you explain it just again? So
Yeah.
the top is your input bits, and the right, what's the right side? The extra?
Yeah, they're just your extra. So generally the extra bits are either tied to ground or to power, but sometimes they're just extra bits that you want to shift into your register or into your whatever you're using it for. So let's say you have 1 0 1 1 1, right? But now you want to have 1 0 1 1 1 0 0. So, or let's have another 0. Okay. So now we have to add these 3 bits. So if we put this into here, right? So our extras will now be tied to ground. And now these bits are now put in. We can even bring these ones over here, right? So now we'd have 1 0 1. Is that the number I put? Yeah, okay. Whatever, good enough, right? And then these zeros are now in your values. So if you want, you can tie this to whatever. In fact, these could be connected to some gates, right? A ton of gates are over here. A group of gates. So those could go into here. It could be whatever you want. But
Is it possible to show like a smaller, like a really quick example, really quick
of
this?
what would the example, like, can you explain like the example of it?
Just input some, like put some bits, like just to show like what the bits and then shift that to, or
Okay, yeah.
just so I see it really. Just trying
I think I should have a page here, yeah. Okay, so let's say this is your A5, A4, A3, A2, A1, A0, all right? And then we'll have your B0, B1, B2, B3. And then however many of these you want to have. Or we'll just call this variable, I don't know, y. Okay, you have a y number of inputs. So if you have a y number of outputs, you need a y number of inputs as your extra bits. So let's say we choose that we just want to tie these to ground. So if we tie these to ground, this will basically just make a multiplier. A multiplier of multiples of 2, right? Okay, so if we shift by, how many do you want to shift by?
Just do.
Okay, so
Make it easy.
yeah, so we'll grab this wire, we'll move it here, grab this over here. And then these two will get into the overflow.
Oh, I see.
And then these two will be grounded.
So you count B0 as like, you start at B0, you go 1, 2.
Yeah.
And then you go, oh, okay. Okay, that makes more sense. Okay. Thank you.
Okay, an incrementer and decrementer, I feel like it's pretty obvious, but it's just an adder with a 1 or a -1. But, okay, so we're just gonna move past that. Ah, CMOS, my favorite. For anyone that says this is not how you make a CMOS, MOSFET, this is how you draw a MOSFET. I will die on a cliff. This is how you draw it. You do not use your stupid arrows or whatever. You draw it like this. It's so much better.
It's the circuits.
Yeah.
It's using this.
You do it like this, or like say this is so much easier.
Oh, yeah.
So much easier to understand.
No, it flows from the drain and the source, the arrow goes to the source. The drain goes kind of, it's just there. We're talking about circuits, but this is completely different circuits, yeah.
So I'll explain a little bit more about this when we get to the next slide. But so CMOS stands for complementary metal oxide. That means it's there for every PMOS, you can have one NMOS, or same way the other way around. Your PMOSs are better at pulling ones or giving out power, while your NMOSs are better at giving ground. I'll explain this a little bit later. Does anybody know what this is? Obviously, this is the wrong way of doing it, but you know, no, it's the wrong way.
It's
What is this?
just this. It's just lost the lost bro. Oh, you want me to actually tell you?
Yeah.
Wait. This is common,
Oh my. It has 2 transistors.
no, it's common drain, bro. That's
It's
how
an
starts.
Yes, it's an inverter.
It's an inverter.
Okay.
I'm teasing, right?
Could you like show how?
Yeah. Oh, next slide. But oh, here's your PMOS and your NMOS. So your PMOSs are always tied to power. If you tie it to ground, they're absolutely useless. I mean, they're basically useless. They're very, very slow. And then these are connected to ground. Yes. Okay. So here is your inverter logic. So let's say you have A, right? Your A is equal to 0. So if you put a 0 into here, think about this inversion bubble as it gets inverted, right? So now you get a 1 through here. But if we go through on here, you have your 0, but it's not getting inverted, so it gets blocked. Yeah. So since you have a 1, your output is then a 1. Okay. Now I want you guys to try to make a NMOS by yourself. Yeah. With transistors, make an NMOS. Oh, or NAND. I don't know. What do you want to do? Do you want to do NAND? What do you want to do? Probably NAND's probably the easiest to start with.
Yeah.
Yeah.
Normalize.
Yeah, exactly. Follow a similar template to that. Do a 2-bit NAND. Make sure you have your N and your PMOSs in the right positions. Riyadh's out here cheating.
Just like that. You have enough. Here. So here. Okay.
I mean, you'll either make it NAND or a NOR. The NOR is just the other way around.
Then I'll just, yeah, but you have the cross or whatever.
So this is your NAND. So just your reverse NAND. I think this should be your reverse OR. So let's go create a truth table. We're going to start with a low and a low. So that's a 0 and a 0. A 0 comes into here, goes through here. Another 0 gets inverted, or let me read this. Your 0 gets inverted into a 1. Your 0 here gets inverted into a 1. So your 1 goes down and out. So then if you have a 0 and a 0 here, these both close, or these both are open, so that there's no ground going through this. So your VDD just goes to your output.
Wait, so if A was one, it wouldn't still go to N?
No.
No, because it inverts the, so if the input is.
So let's try another example.
At the
Yeah.
bottom.
So let's say we have, let's do these, right? We have an L and an H. So we have a 0 and a 1. Oh, you can't even see that. Can you see that?
Yeah.
Okay, yeah. So that 0 gets inverted into a 1, right? So this is now shorted. This one is open, but since this one is shorted, the 1 still goes out. It does. You don't need both. But for the bottom here, this one is open, while this one is shorted while this one's open. So ground can't go anywhere, and it goes back to itself.
Why did it go left instead of right? Like that?
It did go right. Oh, it both work. It doesn't matter. Yeah.
The first example you did with 0, 0.
They both go. They both go out. Because it's getting powered by both this transistor and this transistor. Okay, and then we'll go to the next one. So High low is basically the same thing, just the other. Let me switch colors. Yeah, high low is basically the same thing. So this one's a 1. This is a 0. This one is this one is open. So we cross. This one is shorted. This one is open. This one's shorted. So the ground would go like this, just comes back to itself. VDD goes out. And then finally for the last one where it's high, high. So we get a 0 here. The 0 gets opened. The 0 also gets opened over here. And then the 0 and 0 here will,
They're high.
yeah, the 1 and the 1 here will short and short so the ground can get out. So if we follow that same logic to the NOR, it's the same thing. Instead of, we basically just flipped these over. So we had PMOSs in parallel, now we have NMOSs in parallel. We had NMOSs in series, now we have PMOSs in series. And then to go from NAND to NOR, all you have to do is add an inverter to your output.
So what was that?
You added this inverter to your output of your NAND.
Your name?
Yes.
Oh. You just add what, like 2 inversion bulbs?
Well, you have to put an inverter.
Oh, you just put the, you tie it to
Yeah.
the out.
Yes.
Oh, I see.
Technically, you could do this for your input, but you'd have to use 2 transistors per input, which in some cases you need to do that. But in this class, don't worry about it.
Just
Yes.
that, yeah.
This one?
Yeah.
No.
No. The circle. The circle.
This one?
That's pretty much just an inverter.
It is an inverter.
Yeah. So
You
it's-
put the inverter to the output of the NAND.
Yeah, you put it on the outside.
Yeah.
So that creates an ant.
Yes.
Yeah.
I mean, who would do that? But yeah, you
The
could.
Korean man. Is what you're saying. N-A-N-D. You said N-A-N-D, right?
Oh, and.
Oh, I thought you said an and.
No, this is an and.
I heard the and.
Oh, okay. No.
The and's up top wasn't.
Yeah. No, for in most circuits you'll use a lot more NANDs than you will ANDs because the ANDs require an extra inverter at the end. Okay. Any more questions with this? We're going to do a little bit more. Okay. So noise margin. Obviously your ground will be roughly 0 volts. Your VDD will be 1.2 volts. Okay, so here's the question for everybody. What is considered a safe voltage for GND and VDD?
0 volts for ground, like 27. for VDD. We're just thinking about circuits.
Incorrect.
Right there, 1.2.
It just
What?
is.
Oh,
In the past, it used to be a lot higher, but to
What is the safe voltage for ground? Ground is close to 0. This is 0.
yeah, so right, let's say with your timing chart, right? Because this is exponential, right? So it'll go up very quickly and then it'll taper off. So what's the taper off point here that you can say that this is for sure gonna output a 1?
This is unrelated to circuits, right?
I don't know, maybe. Oh, not electronic circuits, but you might need it for this class. Just take a guess. Yeah.
1.
Actually, very close.
1.1.
I'm gonna guess 1.87.
Do say a multiple. So just do like a percentage from 0 to 100% of these two numbers.
65% of VDD.
65. What's your guess? What are you, Quan?
So,
Just guess a percentage.
okay. Like 90.
90 is correct.
Is 90?
And the answer is 90. Whether you need this for your class or not, I don't know, but I put it there. Yeah. So, yeah, so generally you try to go for 90%, just so you're not in your Z region or your undetermined region. And then for your GND, it'd be like 1.1 something or 0.1 something. Okay. Power dissipation and that one I have no clue. But never learned it myself. So that's probably a Balsara question.
So is that pretty much?
That will be exactly what's on your test.
You.
That added on with a ton of other stuff, of course, but I can do some questions that you have.
So, okay, let's see.
I don't like the floating point stuff.
Okay,
Yeah.
can we do some more floating point stuff?
Yeah.
The one that you, the IEEE standard one,
Yes.
that one's kind of. Then maybe,
Yeah,
Yeah.
'cause I mean, I remember this from like 2310,
Yeah.
but I don't know, I just never liked it.
Yeah, I asked Balsara about it. I was like, I'm surprised you're teaching it in this course. And he was like, yeah, everybody forgot it, so we got to go over it.
Yeah,
Yeah.
I don't remember the name class. Everyone's like, yeah, I remember, but no.
Yeah.
Um,
I assume he's doing the 32-bit. If he does the 64-bit, you have to go be prepared that the numbers will change. Like your exponent's larger and your mantessa is big. Yeah.
For the exponent, what do you subtract from, add to it?
I know for this one it's 128. I don't know about the other one. I think you'll only use 32. It's very rare you'll use 64, but I would confirm with Dr. Balsara and see which one he wants you guys to learn. Yeah, figure out which one he wants you to learn. I assume it's 32. Worst case, you can just Google it. Like your test is no. I don't think anybody goes over 64. I could be wrong.
I'll give you a number, can you do it? 32.75.
32.75, sure.
What's the first step? You say like,
So the first step is to figure out whether this is positive or negative. What's the answer?
Well, it's positive, it's positive.
Okay, so we know that this is positive. Now we have 8 bits. We know that since this is positive, we'll keep that. Now we need to get, we need to convert 32 into decimal, I mean binary. So you start off with 128. Okay.
Is it not supposed to exist?
So it does exist. I don't remember why, but it's there.
I know it's 128 minus.
Yeah.
It's 127 minus.
127 plus.
Yeah, I think,
It's 127, right? It's not 128.
I don't know. Guy,
Yeah, it's 127.
where?
There.
Am I blind?
Step 4.
Step 4, where's 4? Oh, here, okay.
It's 120. Is it not 127 plus the number?
Oh, yeah, yeah, I guess.
That's how many bits you shift by?
Yeah, I always just put it there. I'm like, I don't know why it's here, but it's there.
127.
Okay, sure. Whatever. Okay, so we convert 32 into binary, right? So that's gonna be 1 0 0 0 0 0. No, no.
No, one.
Yeah.
That's right.
Yeah.
Wait.
1, 1.
So 20, yeah, 1, 1. Because we're both numbers.
I think I'm missing a 0.
1, 2, 4. 8,
Yeah,
16,
that's-
32. That's yeah. That's good.
No, it's 1 1.
You have an extra 0.
I do. This is 1 2 4 8 16 32. Yeah, so now we're gonna move our decimal point over. So 1 2 3 4 5. So we move 5. So 5 in binary is 101. So we'll add the 0 here.
So wait, oh, you used.
So we do 127 plus 5, which equals 132.
So that's just 132. Oh, okay. I see. So that's our, exponent, yeah.
Yeah,
To the class,
Wait. Oh, you did 5 and
yeah.
you did 5 plus 127. So
Yes.
that's your exponent.
Yeah, and then that's, yeah.
So now our new value is going to be 1.00000011. So we're going to add that to the end of this. So 0.000011, and then we just trail the zeros. Yeah.
Oh, okay. I get it.
It looks very, it's just tedious. It's
Yeah.
not hard, it's just tedious. This is an open everything, so you guys can, if the off chance you forget it,
For the notes, though, they do
pray
it-
Google can save you.
They do it differently in the notes. You gotta say it in the notes. It's so weird.
What did they do in the notes?
You just have to figure out how you do it, like 2 to the n plus 1, or they have like, just, they just show the proof.
Oh, yeah.
Okay, now, just to make sure we're good, I want to do it the other way.
You want to do it backwards?
Do it backwards. Do a negative number.
No, you're so difficult. Okay. 1.00000011 0
Not that easy.
11010, and then we're just gonna have a ton of zeros after that.
Yep. Okay, it's negative. I'm just paying attention right now, so.
Yeah,
I'll just-
Okay, so we know that this means it's negative.
Yep,
So that's one's gonna be huge.
yeah. So your sign bit is negative, so.
Yeah.
That's 6.
So we have a negative something.
5, 6, 7, 8, so yeah, we have 1, 2, 4. That's just 6, yeah.
So then,
So then if you write 6 in binary, you're using that, so it's
so what is one
plus 2, 3,
that
4, 5, 6.
so something minus 1.7 equals 6.
So 1.7 minus first, it's negative 6 or 6, negative 6 minus or plus 1.7. So it's
Yeah, so it's 6 minus 127, which is
negative
121 negative.
1.7.
So now we grab this value, which is this.
It's 6, right? It's 6.
It's 6 minus 126. So now,
Why for addition, what do you add when it's like, if it was a positive number, would you still do the same?
Yeah.
Yeah.
Would you still do 6 minus 1.7?
No, for positive, you did 6 plus 127, since it's negative, you did 6 minus 1.7.
I thought it was just because you.
I thought it was same.
I thought you just subtracted because you're going backwards.
you are going backwards.
Yeah, so when you subtract, because you're trying to find that 121 part, right? That's the exponent. 121 is the exponent in this case.
Yeah, your exponent's negative 121.
And decimal says 121 is the exponent.
No, in binary, it's 121.
They have to be consistent. Like,
I'll show you in a second. But
they have to be consistent, like, because you're doing something plus 127.
yeah,
Just because it's a negative number, you're subtracting it.
I'd say check the 2310 test
Yeah, I
review,
don't think-
but this is what you do. I don't know why.
I think what they're asking, yeah, is it, we're subtracting because it's a negative number, or are we subtracting because we're going backwards?
We're subtracting because we're going back from.
No, I think it's because it's a negative number.
Oh,
You sure?
really?
I don't think the sign of the number matters too much because you could get a very small.
Oh, no. It's because we're going
Yeah,
backwards.
Okay.
It's backwards. It's backwards. It's backwards.
So for the, like, normally you'd have a big number for positive, or that's.
Yeah. So instead, we can change this. If we, instead of this, if we do like 1111001, I don't know. It's obviously a massive number. Yeah. Yes.
This is just a really small number.
Yeah.
Gotcha, it's because we're working backwards. That's why.
Yeah, yeah, that makes sense.
I thought it was because of the sign bit.
No.
What do you think?
So now, if we, in the blue, we'll have 1.11010, blah, 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 blah.
That's
Yeah. Now we're going to do times 2 to the negative 121.
Oh, okay, gotcha.
And who knows what that is, so we'll leave it there.
Yeah, that makes sense. Yeah. I get it. Do you have anything else?
Wait,
Like, is that everything that's gonna be on the exam?
Yeah.
Sure, 100%.
That's what I was told.
that's those numbers over there, they're not decimal points, right?
No, this is just whatever's here.
And that's like 2 plus.
It's just true.
It's everything in the blue bubble, so like all the trailing zeros.
It's so just assume those are all zeros.
So it'd be 58 times 2 to the negative
Do you have to
121.
write trailing zeros in decimal? After decimal, you have.
After the radix point, you don't. If it's before the radix point, then you do.
So you could.
Yes. It's just that I got it from here, so I followed it. Or got it from here.
Right, but that would be like 2 plus.
Yeah, but you have to multiply by, you have to do this before you can convert to binary. I mean, before you can convert to decimal.
You have, for that one?
Yeah, you have to multiply out the exponent.
Multiply the exponent.
Yeah. So you'd have to move this radix point over 121 times.
Oh,
So because that's an insane,
He's not gonna-
I ain't doing that. I ain't doing all that. Ain't no way.
What were the other topics that was at the bottom?
I'll go up.
Oh, there.
It's power dissipation and accuracy delay. Accurate delay, yes.
He said that was gonna be on it.
Yeah. He might not have taught it yet, but
Oh,
I don't remember. Noise
Okay.
margin. Well, we haven't- I don't think we- Have we covered this one?
I think we briefly covered noise margin, like very briefly.
I
on
think
one of the
so.
slides.
I mean, I can explain noise margin to you,
I mean.
but in a VLSI design term, not in this terms.
Explain it in like dummy version though.
Okay, so let's say you have a wire, right?
Okay.
This is your copper wire. It's 100 feet long,
1,000 feet long.
whatever, 100 feet long.
Okay.
But at the same time, there's multiple of these that are 100 feet long.
Okay.
Got food. Oh, it's hungry. Okay, so in this, there's a capacitance here. Or you know what? I'm gonna. Okay, so we'll just do
Wait, is it related to power dissipation? Is that what that is?
it a little bit, but not really. Okay. Oh, whoops! I got rid of too many lines. Okay, right. Okay, so our purple will be our main line, and then our orange will just be another line that there is. So assume here that we have a ton of capacitors all the way through. And these could be, this is just because there's voltage here and there's voltage there, so it creates like a tiny capacitance, right? Between the wires. So let's say that here, this is charged at 0. But the orange ones just got jumped up to 1.2 volts. So now, due to the capacitances, right here will be a slight jump, and then I'll go back down because of the capacitance.
Yeah.
That's basically what this is. And because it's super, super long, it could go up for a while and take a very, very long time to go down. Yeah. So because of that, instead of your wire giving out a 0, it might give out Z. And yeah, or God forbid it gives out a 1, and your entire circuit collapses. Yeah. No. You will not be getting this in Verilog. Verilog, well, yeah, X, Z, and X is a don't care. Yeah. Oh, that's a weird output.
When I Googled it, I thought it said something about like high impedance or something.
Oh, okay, then yeah, then it's just a Z.
Can you do the homework?
Yeah.
Question number 1.
Well, if you
Or can someone give it to me?
Do you get one? Do you get two?
Yeah.
If you can explain it, then it's fine.
You just did the eight minus.
I need to understand, two, but you can do one. You.
Did you understand that one that explained the eight minus one?
I mean, not like one more time. No, because I'm, I don't.
Oh my god.
It's very similar to what we do. I think it's the same thing that we do. The other way, what we do.
Oh,
Yeah, but what we're doing, what we should want to do is. So we should be like 4x2 or by 1.
oh, it's like 4-2-1 shift.
Yeah.
It's a lot easier to understand if you just do the 4-2-1 shift.
That's what, yeah, I understood it, but more.
We realize it's the same thing that.
It's basically the same thing that we were doing
Yeah,
before.
but it's
Just
hard, it's more abstract.
yeah.
It's not linear.
Like it's the same, like the structure is the same.
Yeah.
I was comparing the two and they're the same.
We're looking at inverters.
No. Or the 4-2-1
Yeah.
and the one that we're shooting from, they're the same.
Okay.
The 8 minus 1 is.
Yeah.
So this is from homework 7. Question 1. A. So for this, we want to create a 2-bit adder / subtractor. Yeah, 2-bit adder / subtractor. So we'll start with this, right? We'll start with a register file or some storage saving. So we'll call this a reg, or we'll do an 8-bit reg. So with this 8-bit register, right? Are you okay, Jenny? For this one? Yeah, sure. I'm just like drawing it out, and then as we go, I'll like clean it up. But what are we doing?
I could have done an 8-bit, that each bit.
Yeah, it should work.
Is that how you're planning to do it or no?
Something similar, but yeah. So now we're gonna have our add / sub, and then we're gonna have our. So how does this work? We have our control lines. The control is an AS for add or subtract, and that's it. Interesting. Okay. So then we'd have the output of this will go into your register, and then you'll have your mux here. That will feed into this, and then the register will come over here to feed back into the mux. Okay. Then you'll have your select. Anything else that you guys think I'm missing?
Why does it go back? Why does the register go back into?
So if you want to like output a different value, so let's say you want to subtract again, or you want to add again.
Yeah. It's like you're labeling.
So that's how you guys do it. In fact, you do add and sub in the same thing and have a select.
Yeah.
It's like for the,
But now you actually have to go do the logic for the inside of it.
that top is a month, right?
So you
Yeah.
want us to, wouldn't, so the logic, so the questions for the logic, you add and sub part.
Yeah.
Right?
Well, the logic for all of it.
You can also choose like what the inputs do. So whenever you're for the register, you just feed the output back in the box, so that way you can like.
Oh,
right?
actually, in this you don't actually need it.
In what, the box?
Yeah, you don't need the feedback in this question. I was reading the question wrong.
Yeah.
So you'll have your input X, and then you'll have your input y. This will go from 7 to 0. This will go from 7 to 0. What am I doing? That's a good question. Oh, right. The mux goes into something. Wait, what am I doing? You need a mux for something. Let me think. Oh, you need the mux to select whether it's an add or subtractor. That's what it was. Yeah. Yeah. Yes. Okay. So yeah, so you have your x and your y that goes into here, and then we'll say your output's q. And then your control line will be a/s. We'll set that 0 equals add, 1 equals sub. Okay, so let's go create that, right? So we can have a 2x1 mux. We can use full and half adders, and then it says we can use everything else. So we'll go ahead and do that. So I will copy this register file right here. We'll keep this the same. We'll keep Q here. Then we'll have our input of here, which will be 8 wires. Then into your adder and subtractor.
I'm not sure if it's right.
I said how I understood it, and
Just draw it out, I'd say.
no, like, so he showed me this earlier. What I thought was that you would just have like the first zip code going to the ladder, but then the max would be the other input between it's like normal and converted, and you know it's two something, and what the max would do.
Yeah.
So the max would be select, would select either Y or Y's to complement for add or subtract.
Yeah.
So that is.
I was thinking the same thing. I think you're right. Yeah. So we're gonna grab a full adder, and we're gonna move this even further over. So we're gonna grab this full adder. So we're gonna put our input x here, or we'll say x0, and then we'll have this mux here that goes into here. We'll have y0 into here, and then y0 not into this one. And then this will be your 0, this will be your 1, right? Yes. So that one will go into here. And then we'll have another mux into this one with the 0, with the 1. This one will be tied to power. This one will be tied to ground. This will go into this full adder. And then this will be into here. And then this will be with your select, which is a/s.
What's the second mux?
Yeah. Let me finish this and I'll do that. So I'm gonna just copy this. Okay. So now we can erase this. Oops.
Those two inputs. These are half adders.
Okay. So this is the rough idea. You're just gonna have to add more full adders for every single bit. Yes. You want me to explain that?
The marks would rather find.
Borba. Okay, so this mux right here. So this is like this is for your two's complement idea, right? Okay, that's gone. So for your two's complement, that's your subtraction. So if it's a 1, it'll power, oh, whoops, this is wrong. It's the other way around. My bad, guys. Good. This will be tied to ground. And this will be tied to power. So if you get an add, it will put in a 0. If you put in a subtract, it'll put in a 1 for your two's complement. In which case your inverted y will go through, which is subtracting, the same thing as subtracting. And then that will go into your register file and your output. I guess you don't even need a register file now, but so you could erase that and then just have this be an 8-bit.
Yeah.
But yeah, so that should work. That's how I do it. Maybe there's a better way. But if you can come up with it. Obviously, I would not recommend doing this why not inverted. Make sure you actually put an inverter there. Don't put y bar. Yeah.
Excellent. Instead of that.
You could.
Yeah, you could.
Can I see that? Well, like how XOR does an inversion or two's complement.
I remember Kogan did this.
Yeah.
I don't remember how exactly she did this, but she did this in class. So this should be a y0 and then your select. I think this is just your select. So in this case, if you have your select as a 0, which would be your add, you'd have a 1 and a 0, which will output a 1, which is good. If your select line outputs a 1, that'd be a 1 and a 1. So it'd be inverted to a 0. So yeah, that works. And then if you have a 0 and a 1, it'll output a 1. So yes. Your XOR would probably be better. Transistor count. I think it's better by 2 transistors. So yes, you should use your XORs. Yes. So both of these technically work, but it's up to you. That looks like an OR gate. That does not even look like an XOR. There we go. That's an XOR. Okay, any other questions?
Except from that one full liar question, I know that you're almost out of time, so.
Are we? I don't know. Let's
You go to 7, right?
no 7:30.
7:30?
Yeah.
Oh,
Your iPad's dead, so I can't scroll through it.
okay.
Well, it turned off.
Oh. I can try that.
Oh, Jenny's so tired.
I mean, maybe just I want to understand that adder.
The shifters one?
Yeah.
The adder shifter?
Yeah.
The multiplier?
Yes.
Yeah, okay. Yeah, we can do that one. Okay. I mean, I know it.
Here's the work. I'm just gonna translate them.
Yeah.
Well, do you want to do it on like an iPad or something so that way everyone else can see it? Or
I thought he was gonna do it. I was just gonna try to.
Yeah.
oh, I see.
So we're trying to, this question, you have an input of A of 3 to 0. So that means it's A3, A2, A1, and A0. And you're trying to multiply this by 7. So you multiply by 7. So there's a lot of ways you can do this. You can just do it this way where you convert the 7 into binary, which would be 0, 1, 1, 1. Which would be A0 here, A1, A2, A3, A0, A1, A2, A3, and then so on. This will give you an output similar to this. It'll be A0, A0 plus A1, A1, A2, A3 all added. Yeah, so I'll have A1, A2, A3. And then this one will just have A2 and A3, and then this one will just have A3. So that's the rough idea. There's a lot of ways we can do this, just putting a ton of half adders and full adders together. We can do it this way, or we can try to do this with shifting. So we're going to do it the shifting way, because that's the question I think everybody had.
I'm just walking. I'm doing it over there too.
Okay. Yeah, so
We're
the
trying to compare, that's all.
so the shifting way is, which one are you doing? The 8-1 or the 4-2-1?
We're doing the 4-2-1.
You're doing 4-2-1? Okay. So we'll do the 4-2-1 as well, and then afterwards we can do the 8-1. Yeah. So this bit is worth 4. Oh, actually, here, let me explain this before I just go for it. So with shifting, the shifting is the same as multiplying, but the shifting only works for something 2 to the power of. Guys, can you be a little bit, chill for a little bit? Yeah. So since 7 is not a multiple of 2, you need to find the multiples of 2 that equate to 7. So in this case, 7 is equal to 4 plus 2 plus 1. In binary, yeah. So right. So this would be the same as shifting 0, or let's call this S0, S1, and S2. So in order to go 4, we'd shift by 2. To go 1, we'd shift, or to go to 2, we'd shift by 1, and for 1, we'd just keep it where it is. So we're going to follow this premises in order to solve this question. Yeah, so we'll go bring it down here. So we're going to draw a full adder for each of them. You'll see why in a second, but okay. So we're going to start with A0. So we see here that we need to shift, or I'll write it down here. So we have 7 equals 4 plus 2 plus 1. That's a bad 4. So we need to shift by 2, shift by 1, shift by 0. So we're going to do that. So here, we'll stay here. And then to shift by 1, we'll go here. And then to shift by 2, we'll go here. And then for the next one, for A1, we need to shift by 1, or shift by 0, shift by 1, and then shift by 2. For A2, we'll grab this color. We need to shift by 0, shift by 1. But see here, we're missing a full adder, so we'll go create another full adder for this. Yeah, so we'll go grab that color, and then we'll add it here. We're going to do the same thing for A3, 0, 1, and then we need another adder. So we'll go do that here. Duplicate, and let me copy this down. Okay, so this would be our last one. Okay, so we've done this, right? We see that we are wasting some transistors. So instead of this full adder, if I copy this over here, you can duplicate this down. Okay. So since this full adder only has one input, That means our output's the same as the input, so we can just get rid of this full adder. And then the same thing over here, we only have one input, so we can get rid of this full adder. And this full adder only has 2 inputs, so we'll change this into a half adder. And then same thing here, we'll change this one into a half adder. All this does is save us transistors, but it doesn't change up any logic whatsoever.
Michelle, could you explain why you doubled that? I kind of missed that. Could you explain like why'd you copy?
Yeah, so I copied it just so you can see the steps. So over here, this full adder only has 1 input, right? And then this full adder over here also only has 1 input. So instead of using a full adder, we can change that into just being a wire, right?
Oh, okay,
Because
okay, gotcha.
0 added to 0 is still 0, or 1 added to
Yeah.
0 is still 1. So we're wasting transistors if we do it that way.
Right. Okay, gotcha.
So we're going to do it like this. So now we have these values. Since A0 isn't added to anything, we can pull this wire straight down and we can call this Q0. That's our output Q. But now we need, and we can do the same thing for this one. Do Q1. But now we have to go worry about the output of these adders. There's the Q outputs, and then there's also the carry outputs for each of them, in case both of the inputs are 1 or all 3 are 1, right? So now we need another set of adders. So let's grab a set of adders right here. We'll start with full adders. We can change it if needed. Let's hope that's enough. I can add more if needed. So in this case, this carry will go over here, while the output of this full adder will come inside. It will come over here. And then we're going to follow that pattern for the rest of these. Yeah. So if we look at this, we're going to follow like the same logic as before. This full adder right here is useless. It does absolutely nothing. So we're going to get rid of it. And we'll just get rid of it. And we'll just keep it as a wire. Oh, I lied to you. That full adder is important. My bad, guys. So that will come over here. It'll be connected to this wire from A3. So we're going to start from right to left. So with this full adder, we only have 2 inputs, right? So we can change this into a half adder. In fact, we can do the same thing for, we can't do that. Let me erase this real quick. I made a mistake. So we're going to move these carries into the top just to make it a little bit easier to understand. So this is just a half adder because we only have 2 inputs. But the carry of this half adder will go into this full adder. And then this output will be Q2. This output will be Q3. This output will be Q4. This output will be Q5. So we do this. We have our carry again, and then our final carry out here will be Q6. Did I make a mistake? I feel like I might have. Let me check here. Okay, so yeah.
Are you done with it?
I need to check if I did it right real quick though.
Michelle.
1 second. One zero zero 1 0 1 1. Yes, so this answer is correct. All right, what's up, guys?
Oh, I was looking at this and I realized that if you make this a half adder, then you get rid of your pieces.
Yeah, it can't be a half adder. You need to be a full adder
Yeah.
because you have the carry in.
side.
Oh, yeah,
Three.
I see it.
Are you sure it's not a Sharpie?
It's a highlighter. I didn't even read it.
Oh, this guy.
Oops. Oopsies. So what are the, so wait, what is this? Is this like just the general overview of what you got, like?
Yeah.
And this is like the final one?
So this is how we started, but we simplified this, and instead of using full adders, we used half adders and wires. So I think on your assignment it said you can only use full adders.
Full adders.
Yeah, so technically you can't do the simplification.
Oh. Because there is this problem to simplify it, you get, like, you get rid of terms. Because like I would, this just be a half adder for me, so I wouldn't have this carry, which.
Wait, why? Let me see.
So for this one, if I make this a half adder, I don't have this carry, so I can just make this a half adder, so I don't even have P6. I don't make it half adder. This is gonna take it down. Sitting over here.
You still need a carry. You still have a carry, even if it's. A background can still have a carry. Background has two inputs to uploads.
Oh, okay. I didn't know that. I thought it only had one. I thought it only had one option.
You guys heading out? You guys leaving? I'll see.
I do think this is the same thing.
You going to Piata? Yeah, I think we're gonna go right after the test review. Are you not going? Oh. Hi, Kimberly.
Any more questions?
Michelle, we were having
I
review.
want to say,
Okay, do you guys have any more questions? Oh, want someone say something in the chat? Is this gonna be uploaded? I don't know when. It'll probably be either uploaded tonight or tomorrow.
All right, I was just asking, just to say.
What's up, guys?
I don't have more questions.
Okay. So if there's no more questions, we can end the test review. We'll leave it up. to you.
Oh,
Has she got anything? Oh, and he's gone. Okay, well, guess that's the end.
That's just three of you.